There is a specific mathematical challenge known as Newton's Claude cycles problem. For years, it sat on the shelf of unsolved conjectures. It involved graph theory and cyclic structures that seemed intractable for standard algorithms. The breakthrough came not from a single line of code, but from a specific type of collaboration between human intuition and artificial intelligence. However, the real story is not the solution itself. It is the architecture required to reach it. To understand this, we must look past the math and into the machinery of human-machine feedback loops. Here is the thing about complex problem solving. The bottleneck is rarely the calculation. The bottleneck is the flow of information. In a traditional setup, an artificial intelligence generates a hypothesis and a human reviews it. But if the loop is too slow, the context evaporates. Imagine trying to solve a puzzle where every time you pick up a piece, you have to walk to a different room to get a new one. By the time you return, you have forgotten the shape of the piece. This is the latency management problem in human-machine collaboration. For the Claude cycles problem to be solved, the system had to maintain a tight feedback rhythm. The human intuition guided the artificial intelligence to reframe the problem rather than asking the machine to solve the graph theory conjecture autonomously from scratch. This hybrid workflow is critical because it leverages the speed of the machine with the direction of the human. If the delay between the human thought and the machine response is too long, the cognitive thread breaks. The human loses the thread of the argument. The machine loses the context of the proof. This is why latency management is not just a performance metric. It is a cognitive requirement for the collaboration to function. Now consider the issue of state persistence. A mathematical proof is not a single event. It is a long sequence of logical steps that can span days or weeks. In enterprise machine learning operations, we call this state management. If the system resets or loses context between interactions, the entire effort is wasted. The breakthrough required a persistent state where the proof assistant could remember previous attempts and logical constraints. This is where the distinction between probabilistic language models and deterministic logical proof becomes vital. The artificial intelligence could generate a conjecture, but it needed a rigorous verification layer to ensure that every step held water. Without state persistence, the system would drift. It would forget the boundary conditions that made the problem difficult in the first place. Imagine a library where every book you read is deleted the moment you close it. You could never build a complex argument. The system had to act as a library that remembers every page turned. This brings us to the role of the proof assistant. Think of the proof assistant as the immune system of the research process. Large language models are probabilistic. They predict the next word based on patterns. Sometimes they hallucinate. They sound confident, but they can be wrong. A proof assistant operates on deterministic logic. It does not guess, it verifies. In this specific case, the collaboration highlights a new paradigm where proof assistants serve as rigorous verification layers for artificial intelligence-generated conjectures. This effectively bridges the gap between the fluid nature of language and the rigid requirements of mathematical truth. The system had to ensure that every time the artificial intelligence proposed a path, the proof assistant checked it against established axioms. This created a safety net that allowed the researchers to take risks they otherwise would not have taken. But in an enterprise environment, you need more than just a safety net. You need fail-safes. When you deploy this kind of agentic system at scale, you must account for the possibility of failure. What happens if the artificial intelligence enters a loop of its own making? What happens if it generates a valid-looking but logically flawed proof? The architecture required for this breakthrough included mechanisms to detect and abort these cycles. This is a standard requirement in machine learning operations, but it becomes critical when the output is mathematical truth. The system needed to know when to stop and when to ask for human intervention. This management of failure modes is often overlooked in discussions about artificial intelligence, but it is the difference between a research toy and a production tool. It requires a system that knows when to trust the machine and when to pull the plug. The insights from this case study suggest that the most significant near-term advances in mathematics will come from agentic systems capable of iterative hypothesis generation and self-correction. This is not about static problem solving. It is about a dynamic process where the system learns from its own errors. The Horizon Math benchmark and the Agentic Researcher Framework establish a consensus that human-artificial intelligence collaboration is successfully tackling complex mathematical challenges. However, neither source provides specific methodologies for the Claude cycles problem itself. This gap in the literature is significant. It suggests that while the field acknowledges the problem resolution, the specific mechanics of this breakthrough remain undocumented in the provided literature. We are left with the architectural requirements inferred from the success rather than the code itself. This leads us to a potential inflection point in the field. The perception of artificial intelligence is shifting from a mere tool for calculation to a collaborative partner capable of discovering novel mathematical structures. The event marks a change in how we view the research pipeline. It is no longer just about the human writing the code or the machine running the simulation. It is about a hybrid workflow where human intuition guides the artificial intelligence to reframe the problem. This requires a specific type of infrastructure that supports long-term memory and rigorous verification. Without these architectural components, the collaboration would fail. The latency would be too high and the state would be lost. We must also consider the implications for the future of mathematical research. If this architecture can be replicated, it opens the door to solving problems that were previously thought intractable for current large language models. The Claude Opus demonstration showed a capacity for mathematical reasoning that exceeded previous benchmarks. It successfully navigated complex logical constraints in a cyclic graph problem. But this capacity relies on the underlying system design. It relies on the ability to persist state across sessions and the ability to verify outputs in real time. These are engineering challenges as much as they are mathematical ones. As we look forward, the most important work is not just solving the next conjecture. It is building the systems that make solving them possible. The focus must shift to latency management and state persistence. We need fail-safes that protect against hallucination without stifling creativity. This is the new frontier of machine learning operations. It is where the theoretical power of artificial intelligence meets the practical reality of enterprise deployment. The Claude cycles problem is a proof of concept. The real work is in the architecture that made it possible. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.